He's cool.
Thank you very much, everybody, for showing up to today's talk.
You're right.
We have with us Dr. Sabieh Anwar, uh, and this is really a formality because the talk is being recorded. Everybody here knows him already, so but I still need to introduce him. Uh, Sabi's research interests encompass spintronics, magnetism, and optics. He's published many papers of the order of 100 in international journals of repute. In addition to this research, he has really focused on establishing uh, uh, lab facilities, first within LUMS, and then many of his ideas have been implemented in around 10 universities in Pakistan. So today's talk is also related to the work done in Phys Lab, as I understand it, but of course, Sabi will tell us more about it. Uh, he is the General Secretary of the Porzani Science Society, which is focused on science popularization. And the Lahore Science Mela is everybody's favorite event. And unfortunately, I missed it this time around, and I heard that this one was bigger than ever before. So it's great that this initiative is increasing. We Mr. Sabi is currently the a professor of physics at LUMS. He has also worked as dean here. Over to you.
Thank you, Rizwan, for the generous introduction. So today I'm going to talk about three different ideas that are really not just my ideas, but these are ideas which have input from many students, many group members, staff members, visiting students. And I've kind of picked up three examples from the Phys Lab, which I find to be very interesting because not only that these experiments are very simple in their hardware sense, but they also harbor rich physics, complex phenomena, and they are a rich tapestry for deep research. So, and I've kind of labeled my talk in honor of two physicists and one theologian from the 18th and the 19th century. All three were from Great Britain. The first idea I would like to cover is that of a very unique pendulum called the Wilberforce pendulum. Wilberforce, of course, is the name of the person who first came up with this idea. So on the left, you can see one of the kind of first Wilberforce pendulums that were made by some manufacturing company in the UK. The Wilberforce pendulum is simply a pendulum that is capable of doing both compressional motion, that is it can do longitudinal oscillations, and it can also do torsion. So it can twist and extend at the same time. So it's a very simple contraption. So the basic idea is that we can. Uh, I don't know how to play these videos. Mm, does anyone know of a mechanism to? So these are really videos. So is it possible?
Is this a PowerPoint presentation?
This is a PowerPoint presentation.
Play.
If I turn this off. And slideshow. Hmm. Okay,
Is
so
it playing from here?
yeah, it's playing from here.
So let's just keep it like this for
Okay,
now,
okay.
and then we can move to the slideshow.
So this is, as you can see in this video, a, a pendulum is the pendulum is oscillating and it's twisting at the same time. So the experiment really itself is very simple. You just analyze this motion, and you analyze its motion through video. So you put a camera in front of this pendulum and take a live video. Likewise, here is another example. So this pendulum is oscillating, and even though the impact is imperceptibly small, when it ceases its longitudinal motion, its torsional velocity goes up. So there is coupling between torsion and oscillation. So so it's basically 2 degrees of freedom that are at work here, and these 2 degrees of freedom are mutually coupled. It's just like coupling two pendulum, two harmonic oscillators, and so on. So why is this idea so fascinating? The idea is fascinating to me because it exemplifies another idea which is ubiquitous in quantum physics, and that is the idea of avoided crossings. So, in order to invoke what we really mean by avoided crossings, let me give you a very simple example. So, I'm going to shift gears here a little bit and try to bring in some very simple quantum mechanics. So, if we have two spins that are uncoupled, two independent spins, and let's assume, yes.
Could we shift the video to your
All right, okay.
laptop, because I think that would be better. So,
Mm, okay, I think I just need to move to.
yeah,
So, just need to.
integrated camera.
All right, okay.
Yeah, I think
Now,
that'd be better.
share
Thank
screen
you.
again. All right, so in this particular example, what you can see is there are two spins. Each of these spins we assume is a spin half particle. So it has a particular Hamiltonian. And the coefficient with each of these Pauli matrices is something that depends upon a parameter. And I have parameterized this coefficient with the variable epsilon. So it's just like a spin placed inside a magnetic field. And there are two spins. Each of the spins has their precise Lamo frequency, its own characteristic frequency, which is given by gamma b over 2 into some parameter, 1 plus epsilon. And the parameter is the same, but the two spins have different frequencies. One is identified by plus epsilon, the other is identified by minus epsilon. So these are two selectively addressable spins placed inside a magnetic field. And this is a technologically important Hamiltonian because whenever you do an experiment like NMR or FMR, the spins are placed inside a magnetic field, and each one of these spins is addressable by their characteristic frequencies. But the point here is that the two spins are uncoupled, they're totally independent. So these are two independent qubits or two independent spin half particles. And if you look at the spectrum of corresponding to this physical system, of course, you'll get four eigenvalues, four eigenstates, and these eigenstates are simply the eigenstates of the Zeeman Hamiltonian. So they are angular momentum eigenstates. And we can label them as E1, E2, E3, E4. And if we plot these eigenvalues in terms of the parameter epsilon, we see that two of the eigenvalues remain constant. They're independent of the parameter, 1 and minus 1, whereas two eigenvalues are dependent on the parameter, and there's asymmetrically dependent on the parameter. So one eigenvalue increases as epsilon, and the other eigenvalue changes in the negative sense. And both of these eigenvalues have a crossing. So these eigenvalues cross whenever the parameter is zero. So this is called a zero level crossing. And in most cases, it's also called a degeneracy. So there's a degeneracy in this spectrum. Now, if I were to change the Hamiltonian a little bit and add a coupling term to this Hamiltonian, in which the two spins are now mutually coupled with one another, uh, and do observe that this extra coupling term commutes with either of the other two terms in the Hamiltonian. So at best, what this coupling term can do is just shift the bias along the computational axis. The energy values would just shift up or down, and the overall structure, the eigenstructure of this problem, is not going to change. There is still going to be a crossing. Now it's not, it's still a zero. It's not a zero level crossing, but the crossing does occur whenever the parameter is zero. But the value of this crossing is not at zero. So there is a genuine crossing inside this eigenvalue spectrum. But there are additional, of course, there are additional crossings here. So there's a, in both of these examples, there's a crossing here and a crossing here. So all in all, there are 5 crossings. So these crossings are really important in physics, and they come up in different applications. Just to give you a simple example, if you have a system in a quantum state, which is in an eigenstate of the Hamiltonian, suppose this green eigenstate, and you change the parameter slowly, which means you do an adiabatic transformation, and you hit upon a zero crossing and keep the adiabatic evolution, a Berry phase is picked up, a geometric phase is picked up. So crossings have a really important role to play. In graphene, for example, there is a zero level crossing at the k equals 0 point at the center of the Brillouin zone. But you kind of open up this gap a little bit, which means if there is a shallow avoidance between the crossings, new optical properties can appear. There are hidden symmetries at a crossing point. And by hidden symmetry, I mean, according to the Noether theorem, whenever there is a hidden symmetry, there is always a conserved quantity which corresponds to a Hamiltonian. Hidden symmetries means that there is a Hamiltonian which is a constant of motion, which is not an eigenstate of which does not commute with the other parts of the Hamiltonian. So there could be hidden symmetries at crossings as well. So crossings are really important, and more so in atomic physics and condensed matter physics. So we would like to study crossings. However, if I apply a coupling which does not commute with the original two terms in the Hamiltonian. So now this is a coupling between the two spins, which is not along sigma 1z, sigma 2z. Rather, it has these additional sigma x, sigma 1x, 2x, sigma 1y, sigma 2y terms. So instead of now an Ising Hamiltonian, we have imposed a Heisenberg kind of Hamiltonian. So this additional coupling term does not commute with either of sigma 1z or sigma 2z. Okay? So now this is a different kind of coupling. And now if you would like to do an eigenvalue and an eigenstructure decomposition of this Hamiltonian, we'll still get 4 eigenstates, 4 eigenvalues. And 2 of these eigenstates remain equivalent to the original. These are the Zeeman states corresponding to the maximal magnetic contour number states +1 and -1, whereas two of the eigenstates E2 and E3 are now superpositions of uh, of these oppositely flipped eigenstates. So now the eigenstructure changes. If I were to define a new parameter theta, which encompasses alpha, where alpha is defined by this coupling parameter, the strength of the coupling is dependent upon J. And I've reparameterized the coefficient so that J has units of frequency. So this coefficient J is kind of the strength of the coupling. And if I divide this by the uncoupled uh, coefficients which depend upon gamma b, I can define a coupling parameter alpha, which is a signature or a measure of the coupling. So in this case, I can reparameterize the Hamiltonian in terms of a new variable theta, okay, which is really a measure of the coupling strength. And I can put up all my eigenvalues in terms of alpha and theta or epsilon and theta. So these are the four eigenvalues. And if I were to draw these eigenvalues, uh, this is structure that I get. If my, remember that alpha now is the strength of my coupling because it's proportional to J. If my coupling is really small, say I put it at a minuscule 0.001, uh, I would get something like, it's a very shallow crossing, but at this scale, it just appears that there is a zero level crossing. But if you zoom in, there will be an extremely tiny uh, avoidance, a tiny gap between the two states, which is amplified when I've plotted these other three instances when my alpha is zero point 0.1, zero point 0.2, and zero point 0.3. Here you do see a gap. So this crossing now opens up and a gap is produced. This is called an avoided crossing. Crossings are now avoided because of the coupling between the two spins. Higher the coupling, larger will be this avoidance. So, and if alpha keeps on increasing, the number of crossings and keeps on changing. For example, in this example, there's a crossing here, a crossing here, a crossing here, and a crossing here, and an avoided crossing at epsilon equals 0. In this case, when alpha is zero point 0.3, two of the crossings disappear. So by just looking at the eigenvalue structure, I can also find out the number of crossings. And this is, by the way, is a four-dimensional Hilbert space. So the number of crossings is limited. It could be at the most 10, by the way, crossings plus avoided crossings. But for multi-dimensional systems, say you have a spin half particle and a spin 3/2 particle, or you have multiple qubits in a quantum computer, or you have a complex molecule which is emitting light and you're doing spectroscopy with it, the number of avoided crossings and crossings can really reach up to the hundreds. Okay, so this is a simple problem just to kind of elaborate what crossings are and avoided crossings are. So if I were to do further analysis of this problem, and I've just drawn this structure for alpha equals zero point 0.1, I do see that this opening of the crossing, this avoidance of the two levels, is of the order of the coupling parameter for alpha. So higher the alpha, higher the coupling, higher will be this opening. And the eigenstates are now, we do know what the blue and the red eigenstates are. These are the maximal angular momentum states, spin 1 and spin -1. And the other two angular momentum states which have spin 0 are really superpositions. So and the superpositions are, of course, are written here, and they depend upon the coupling strength. And the coupling strength is determined by theta, and its in place determined by the parameter. So wherever this parameter is 0, the eigenstates are the singlet and the triplet states, S naught and T naught, with angular momentum, total angular momentum 0. And far away, when the parameter epsilon is large, either positive or negative, then each of these eigenstates adiabatically evolves into these computation states, into these Zeeman states. Okay, so if I were to suppose I had two spins which are coupled, and epsilon is very large in the negative sense, and my system is in equilibrium, so it's in an eigenstate of the Hamiltonian, and I change the parameter such that the Hamiltonian evolves really smoothly, then according to the adiabatic theorem of quantum mechanics, the state always remains in an eigenstate of the instantaneous Hamiltonian. And this evolution is really small. So as the Hamiltonian changes, the system remains inside its instantaneous eigens in the instantaneous eigenstate of the Hamiltonian. So it evolves adiabatically. So it keeps on moving along this curve on the eigenstructure. And the evolution is really small. So you have to satisfy the constraints of the adiabatic theorem.
Evolve ये epsilon के
Parameter, you're changing the parameter epsilon, which means you're really changing the magnetic field, or you're changing the asymmetry between the two spins.
वो state है and
So very far off, when epsilon is very large, the state goes into this state. The state is changing its form. It's also called parallel transport. So you are, if this were a single spin, you're doing parallel transport on the block sphere. But now you have two spins, so the state starts off in an eigenstate of the instantaneous Hamiltonian. The Hamiltonian changes state is following, tracking the Hamiltonian. Okay, so it keeps on. So it's just like you are wagging a dog. The dog is your eigenstate, and if you move slowly enough, the dog keeps on following you, while the length of the rope doesn't change. Okay, so this is adiabatic evolution, and this is really important for many technological applications. It's important for quantum computing. It's important for many kind of spintronic experiments as well. So this is the overall structure. But the key point I want to highlight is that this crossing is now avoided. And in fact, you can find out the number of crossings, you can find out the number of avoided crossings. So one way to do that is that you look at this Hamiltonian and determine all its eigenvalues, and then you kind of majorize the eigenvalues, which means you sort out the eigenvalues from in ascending order, and all of the parameters are real, so we assume that, and the Hamiltonians are real and symmetric, so we are assuming that the eigenvalues are also real. So you sort them out, and then you compute this product of the squares of the difference between two eigenvalues, and let's call this product the discriminant of the Hamiltonian. It's a loose term, but let's call it the discriminant of the Hamiltonian. Geometers use this term, and find out d whenever, and find out this d. This is, for example, the d for the two coupled spins, and then you find the roots of this polynomial. If the roots are real, you'll have a crossing there. And if the roots are complex, then the real part of those complex roots will show you the location of the and the number of the avoided crossings. So this is a general algorithm by which you can calculate the number of crossings and the number of avoided crossings and where do they exist. In fact, you don't even have to calculate the eigenvalues in many cases. If you do an expansion of the characteristic polynomial corresponding to the Hamiltonian, h minus lambda I, take the determinant of this and expand this in terms of your parameter lambda, then the coefficients can tell you where, can help you determine this discriminant. So you don't have to really find out the eigenvalues. Finding eigenvalues is complex for large systems. So there are algorithms by which you can easily find this determinant. And Mathematica has a very nice function as well. So this is how you calculate. For example, for the two coupled spins, you have complex roots, which with the real part 0. So you have an avoided crossing at epsilon equals 0. You have real roots at 1 minus 4 alpha square root plus minus, so it gives you plus minus 0.775. So you have two crossings at minus 0.775 and another crossing at plus 0.775. Likewise, you have crossings at 1.18 for this particular example for alpha equals zero point 0.1. So this is how you can determine the crossings and avoided crossings for a whole variety of Hamiltonians, even if they're very large dimensional. And another route is that you can, since all the roots are, the discriminant is always greater, is always positive. So if you take the log of d plus 1, this will always be non-negative. And by looking at the location of the zeros of this logarithmic function, you can also determine where the roots are. So this is this blue curve, this magenta curve at the top, plots this function, this logarithmic function, and by looking at the location of the zeros of this function, I can also determine where the roots are. And okay, and where the and the this minimum is telling you where an avoided crossing is. So so these are just algorithmic recipes. Now we come back to our Wilberforce pendulum. These avoided crossings abound in quantum mechanics, condensed matter physics, atomic physics, molecular physics, and you'll see example upon example of crossings and avoided crossings. Whenever you do a density functional theory calculation, you look at the band structure, you'll see many crossings of this kind. Now, what does this have to do with the Wilberforce pendulum? Now, it's a coupled system, 2 degrees of freedom. There's a torsional degree of freedom and a vibrational degree of freedom. And we can write an equation of motion, which is simply the Newton's equation for each degree of freedom, for the z degree of freedom and for the theta degree of freedom. And if this term is included, which couples the z and the theta part with some parameter strength epsilon, this is what the two simultaneous differential equations would look like for the system. Now, what we do expect is that if there is coupling between these 2 degrees of freedom and we find the normal modes of this coupled system, we'll get an avoided crossing. So we're trying to explore whether we get an avoided crossing inside a mechanical system. And that mechanical system in our case is a Wilberforce pendulum. We can have other examples. We can have acoustic examples. We can have two harmonic oscillators, two linearly oscillating springs that are coupled to one another, and so on. By the way, whenever there is an avoided crossing in the quantum domain, there is always also this possibility of quantum chaos as well. So this is a very rich field. So let's look at the Wilberforce pendulum in the light of avoided crossings. So here are the two equations of motion. Now what we would like to do is we would like to find out the normal modes of this coupled system. This is something that you easily do in your basic mechanics, classical mechanics class. By the way, omega z and omega theta are parameters of the system. These are the natural modes of the uncoupled system. Okay, k spring constant, mass, m is the mass, delta is the torsional constant, and I the moment of inertia. Okay, something really simple. And then I just kind of eliminate the z part and write and express everything in terms of theta, and I propose an ansatz of this kind, and then I solve it. I get this characteristic equation with a polynomial on the left hand side. I put it equal to 0, and I find the roots of this equation. So I'll get omega 1 square is one normal mode frequency squared. Omega 2 square is the other normal mode frequency squared. By the way, I think there's a typo here. One of these should be a plus sign here. Okay, it's a typo here. Now, each of these normal modes represents is dependent upon the moment of inertia, the coupling strength, and so on. Okay, so there are structural parameters, and so if I plot these normal modes, I get exactly the same behavior. I get, if there is coupling, if epsilon is non-zero, I'll get an avoided crossing. Okay, so if I were to do a dimensionless plotting of the two normal modes, I just use a small coupling parameter 0.1. These are the two normal mode frequencies squared. There is an avoided crossing. Okay, I can also take the square root and parameterize in terms of hertz, in terms of frequencies. There's an avoided crossing. If I take realistic values, which I do not know beforehand, but I can do an analysis of the videos, and I'll show you how you're able to do that. If I put in these parameter values, the numerical values from the system that we have in our lab, we can also plot these in the dimensional sense, and we get an avoided crossing. These are the moment of inertias, and this is our real data. These plots, these data points, the blue and the orange data points are real data from different kinds of Wilberforce pendulums. So my variable of interest, I change the moment of inertia of the pendulum, and I look at the normal modes and demonstrate that these avoided such an avoided crossing does exist. So these solid lines in this plot are just a means. These are just guides to the eye, by the way. Okay. So this is experimental data, and these are of course plots from the mathematical exposition. Now I can. How do I estimate the parameters for this complex system, for this coupled system? This is a very sensitive system. The values for the spring constant, the coupling are really, really small. So it's a very sensitive system. So what I could do, I could take the square of each of the normal modes and subtract the squares and then take a overall square again. I get a quadratic equation in 1 over I, in the inverse of the moment of inertia. So if I vary the moment of inertia of my pendulum, and I find out the normal modes, and I plot this difference of the squares of the normal mode squared with the inverse of the moment of inertia, I'll get a quadratic equation. And from the coefficient of that quadratic equation, I can estimate the coupling constant, I can estimate the spring constant, and the coupling parameter. And I'm able to do that, in fact, by different techniques, as I'll show you in a minute. So how do I vary the moment of inertia? I just use different series of objects with identical masses, because mass is also a parameter. Identical masses, but I tune the radius and the kind of dimensions of this object so that the moment of inertia changes in some controllable fashion. I make a table and then I machine different kinds of objects according to the proposed dimensions, and just put them inside a Wilberforce pendulum with the same spring and take a video. And when I take a video, I use our software Phys to analyze the video. And this video is just looking at the center of mass motion. But now, since this is a coupled system, the normal modes will appear in the center of mass motion, in the z motion, and they get different trajectories in time. So for different objects, different moments of inertia, I simply get these trajectories in time. So I get all of this data. The software is capable enough to kind of remove the background noise and just focus on the pendulum, find its centroid, and kind of pick up the trajectories over the course of time. So these are the trajectories of the Wilberforce pendulum for varying moments of inertia, identical masses. And then the next step, of course, is to find the normal modes. So one has to do a Fourier transformation for all of these time trajectories, and you can find the normal modes. And here it's really, really obvious that you see two normal modes in the coupled system. And these two normal modes, if you come back to what we expect, these two normal modes approach one another, they kind of come together, then they avoid one another and diverge. So we see exactly the same behavior inside the Fourier transform data. So one of the peaks, the two peaks are getting closer together, the spacing is decreasing, they touch and then they move apart. Okay. So we do see this phenomenon when we do a Fourier transformation. By the way, for students, I would like to ask a question is, so in the data, in these two data sets for E and F, we also see these small undulations on the Fourier transformation, these small kind of humps, whereas we do not see these humps on this data. So can you guess why this is the case? And I move back to the time trajectories so that you're able to understand, probably answer this question in a better sense. So look at ENF. Now in ENF, I've truncated the data before it has gone down to zero. So truncation the data means that I have a decaying function and I multiply this with a step function. And when I multiply this with a step function, if you know the convolution theorem, when I do the Fourier transformation, the step function has a Fourier transform, which is a sinc function. And the decaying exponential has its own peak. So according to convolution theorem, I'm doing a convolution of the decaying of the Lorentzian peak with a sinc function. So each of these Lorentzian peaks takes up these sinc-like wings. Okay. So this phenomenon is also called the Gibbs phenomenon. The Gibbs phenomenon. All right. So there are lots of nuances about signals that you can learn from this Fourier transformation process. But the key is that even inside this coupled mechanical system, you do see avoided crossings. And if I were to plot, of course,
And so that's an artifact of.
that is a consequence
Right.
of this truncation. I haven't let the
Yeah.
amplitude go down to zero. It hasn't damped fully, and I've truncated it.
But so can I ask? So I would assume that if you truncate any of the others, you would see the same kind
Exactly.
of things over there as well. But can I ask the reason of not having data for more time here, experimentally? Like, so for all the others I see, you go all the way to 200 seconds or so, but here the data is stopping at 100 seconds.
I think the reason for this is if you look at F, the damping is rapid, and beyond this, you do not see any further decay. So the noise level is very large in this case. But here you see the amplitude is starts off from a large value. So it was basically the initial conditions with which these pendulums were launched. So here the amplitude starts at 50. Here the amplitude starts at 10. So you've already, I think the video has not
Right.
been launched from an earlier time. It's just started midway in between. So you're very close to the noise level. So this noise level is probably the same as this noise level. So you have smaller data here, smaller amount of data here. So if you plot this difference of the squares of the normal mode frequencies, you get this parabolic curve. And by the way, this parabolic curve, even though it appears to be very close to zero, it's not really zero here. So it's slightly above zero, and that will give the value of C naught. And from that C naught, you can determine the value of K. Okay. So there were different students who performed this experiment with different pendulums, different springs, and this is the range of values that they obtain. We can also plot the squares, the difference of the squares. We can plot the s- sum of the squares. We can also plot the product of the squares. So if you just have these values for the f1 and f2, uh, here you can take the sum, you can take the product, and each of these cases will probably give you an alternative derivation of the parameters, right? So these different values, and since this is a noisy system, some parameters are less sensitive to the approach in which you measure, and others are more sensitive to the approach by which you determine their values. We've also tried determining these values using machine learning and parameter estimation, okay, and as well as Kalman filtering.
Okay, can I ask another
Yes, please.
question? So here we're talking about the spring constant as being one of the parameters.
Yes.
And whereas you are determining this in a dynamic scenario,
Yes.
the spring constant could also be just determined by just simply loading the spring.
Exactly.
So did you try doing that and comparing with
Yeah,
these
it's
results?
comparable. It's comparable. And the other interesting thing is that it's very hard to this parameter, the epsilon parameter, is really really hard to determine by any other tech. I do not know of any other means by which can determine this
Yeah, I
coupling.
mean it's
And the uh, so the order of magnitude estimates for epsilon is comparable with the data that different students obtain. The second effect I would like to mention is an experiment to do with fluids. This is the Marangoni effect. Now, we all know that surface tension is really important, and surface tension is the internal cohesion between molecular forces inside the liquid. So that's why on the surface, the molecules would behave differently from the interior. That's why a molecule on the surface of a liquid experiences a net pull towards the interior of the fluid, and that's why the surface behaves differently. It's hard to pierce into a surface because of this reason. And this is the phenomenon of surface tension. Surface tension has really lots of industrial uses. It's a really important phenomenon. Something as simple as the shape an object takes when it is perched on the tip of an opening or capillary or a needle or a syringe, that helps us determine what the surface tension is. So depending upon the volume of that fluid, the drop can acquire different kinds of shapes: pear shapes, elongated pear shapes, obtuse shapes, pendant shapes, and so on. So we can do lots and lots of experiments with these drop shapes and sizes. The idea is again very simple. You just perch the drop on the tip of a capillary or a syringe and image it, and then you do an analysis of the shape using some software, and analyze using concepts from a static equilibrium on what the shape should be given a particular value of gravity and a particular surface tension. So for example, different liquids, so in this example, three different kinds of liquids are perched, and a pendant is made from those liquids, and they are perched from identical capillaries. The shapes are totally different. In fact, we could do a large data. We have acquired large data sets on different kinds of fluids. This was a project that came from the industry. They wanted to analyze different kinds of inks and the viscosities and surface tensions of these inks. So we developed a system for that particular industry. So and the technique was very simple. The size and shape of this drop also depends upon the internal diameter of the syringe and the needle, for obvious reasons. The setup is really simple. It's just a camera, once again, that is taking an image of this pendant. You can do all kinds of experiments. So you can find out the bond number of a particular liquid, which tells you the relative ratio between gravity and surface tension. So it's a fraction between forces due to gravity, energy due to gravity, and energy due to surface tension. And as you can see, different diameters, objects of different diameter give you different surface tension. So if you plot versus bond, so each needle size gives you a particular bond number. A bond number is just a measure of the shape. Is this dimensionless ratio that I've mentioned: surface tension and gravitational energy. So each diameter of the needle gives you a different bond number. So all of these tip sizes cluster uh, the surface tension data into particular groups. So for example, this is the 0.55 millimeter needle. This data corresponds to the 0.67 millimeter needle. This corresponds to 1.2 millimeter needle. And then you can do this for different kinds of liquids. You see this very nice clustering effect. This dashed line shows the values of the surface tension taken from a standards book on surface tensions, standard handbook. Okay, so all of these points you can see are also tightly focused around the published values. These bottom curves show another dimensionless parameter called the Worthington number, which is which is the bond number, but you also take into account the volume of the fluid inside the drop. Anyway, the surface tension is really important. So this is the prelude to the Marangoni effect. But surface, so if you have a liquid with different components, different kinds of liquids, and there's a variation in the surface tension of those liquids, what will happen to the fluid? So if, of course, diffusion is always taking place, but diffusion is due to Brownian motion. Diffusion is due to this random motion. But on top of this diffusive motion, there could also be a gradient in the surface tension. So an object or fluid has to move along that gradient in the surface tension, because, and what it would do is that it would move from the low surface tension area region to the high surface tension area region, because you can imagine that the fluid would like to spread in the low surface tension region, but it would like to contract and coalesce inside the high surface tension area region. Okay, so that's why when you take soda or carbonated drinks, you will see these tear shaped, or even coffee, you can see these tear shaped drops that cling to the surface and they kind of move upwards. So surface tension gradients are also an impetus to the movement of a fluid, and the fluid would like to move from low surface tension to high surface tension. So this is the basic principle of the Marangoni effect. There could also be temperature gradients in the liquid. A concentration gradient simply gives you diffusion. But on top of that concentration gradient, you can have gradients of surface tension, gradients of temperature, gradients of potential energy just due to sloping surfaces, and so on. But the Marangoni effect is primarily due to gradients in the surface tension.
So right now we're talking about, let's say, um, any liquid in some container, and it would be visible in that kind of thing. Uh, isn't it also, so there should also be an effect of differences in specific gravity of the liquids.
Specific gravity is really the density of the object,
Yeah.
and that density controls the viscosity of the object. So viscous forces do play a role in how quickly an object can move, how quickly can an object, how easily an object can respond to gradients in the surface tension. The specific gravity controls the viscosity.
My real thing was when you talked about mixing different liquids. So if you have, let's say, a mixture kind of a thing, then is the Marangoni effect related to some kind of a mixture, or is
Yes,
it so
right.
in a mixture, if the specific gravities are very different from each other, or if they're closer together, where would you see the Marangoni effect more? As you'll explain it more, maybe it'll become
Yeah,
clearer.
so whenever there is a larger gradient in the surface tension, the Marangoni effect will become stronger,
Yeah.
and it may become chaotic as well. So in the experiments that we do, we would like to restrict this chaotic motion so that something remains controllable and measurable. That's why we put a hydrophobic surface as well, as I'm going to explain in a minute. So that controls this chaos. So just to give an example of surface tension, so diffusion always takes place, by the way. So you cannot stop diffusion. That's a kind of concentrate. Whenever there's a concentration gradient, there is an outward flow of liquid. So here I have alcohol, colored alcohol, or a dye, or a dyed alcohol, or a alcohol with ink, isopropanol, inside a very shallow film of water. Now, alcohol has ethanol, or isopropanol has a low surface tension as compared to water. Water is one of the substances that has the highest surface tension. Surface tension kind of is so there's a gradient of surface tension, and you can imagine that the water molecules which are in a higher concentration outside this alcohol, they're pulling up on this film of alcohol, because, and they're causing this outward flow of alcohol from the region of low to the high surface tension area. That's why this fluid is spreading. So now you have two liquids, ethanol and water, and both of them are polar molecules, so they mix very well. They're miscible. So you do not have this, and the specific gravities are also very similar, by the way. So you have this gradient of surface tension, and the alcohol kind of spreads out. Now the Marangoni effect is that if you take this water and isopropanol mixture and put it on a very shallow film of oil. Now oil is hydrophobic, which means oil has this functional group which does not like to stick with water, with polar molecules. So it kind of keeps the water away. So now if you put this isopropanol water drop and perch it on a very shallow film of oil, let's see what's going to happen. And this is here where we see this outward flow due to the surface tension gradient in its full glory. And that's where we call this effect, this spectacular effect, the Marangoni effect. Okay, so let's see what happens. So here is this shallow film of oil. So now I think in order to play the video, I have to move out of this for a minute. Let's try to play this here. So let's see. So this ink dyed water plus isopropanol mixture is perched. And now you can see that this is a mother droplet that expands first and then it contracts. And there's a daughter droplet, daughter outer periphery that keeps on expanding. But with time, the interface between the mother droplet and the outer droplet breaks up or fragments into these small drops. Okay, so let's replay this. Or let's look at the next slide, which has other videos. So here is another video. Now, in this particular case, the isopropanol to water ratio is less than 35%. When there is not enough isopropanol, this Marangoni effect does not take place. And the critical threshold analytically determined is 35%. So in this case, there is no Marangoni effect. However, at the critical value of 35% isopropanol, the effect does begin to take place. So this is 35% alcohol. There's a mother droplet that expands, a daughter droplet that also expands, and then the mother droplet shrinks, coalesces inward, and in its wake, it leaves a large number of tiny droplets. Okay, and I'm going to explain the mechanism behind this. Sorry. Let's look at these data. This is less than 35%. There is no Marangoni effect. This is at the verge of 35%. Let's see. Okay. This is even a higher concentration. Okay, now let me explain this. I think I need to move back somehow to 8 minutes.
You go to the same screen and
Yeah.
do start slideshow.
Okay. So now what's really happening is, if I were to explain this phenomenon, there's a mother droplet that is expanding, and then it starts to compress. And there's an outer periphery as well. So there is this hypothetical outer droplet that is expanding with time. It's continually expanding with time. But as the mother droplet condenses inward, it shows this retrograde inward implosion. It leaves in its wake a large number of droplets. And these droplets do not coalesce, they remain droplets. So, what really is happening? So, this schematic shows the process. So, in the middle, this purple region, this is predominantly alcohol. And the alcohol has a lower surface tension than water. So, this mother droplet is expanding outwards. Now, when it expands outward, we do know that ethanol has a very high vaporization rate. It evaporates very fast. So when it evaporates, and there's more fractional evaporation. more fraction of the ethanol that is on its outer rims evaporates. Okay, as a reason, the surface tension outside keeps on increasing because then the fraction of water goes up. So this rapid explosion of the mother droplet is happening. So it's spreading, and it then spreads faster and faster. Okay, because as it evaporates on its outer rims, the concentration of water keeps on increasing because the alcohol has evaporated. So that's why this mother droplet expands. But as the mother droplet expands, there's a particular thickness of this mother droplet. As it expands outwards, if you do a cross section of that droplet, it's thinner at the outer ridges. And when it's thinner at the outer ridges, structurally that ethanol film, that isopropanol film cannot sustain itself, so it breaks down. So just imagine a droplet having a long tentacle, which is far off, and it's thin. So as it tries to be thinner, it kind of breaks off from the from its origin. It no longer remains structurally stable. So it breaks down into these small droplets. So this is the break. This is called a ridge instability in fluid mechanics. This is called a ridge instability, and you can predict when this ridge instability happens. So at this point of ridge instability, it breaks down into small droplets. But those droplets do not coalesce into one another because there is oil outside, and oil is hydrophobic. So these droplets remain droplets. And the mother droplet, since it has lost some of its alcohol, because the connection with the outer ridges has been severed due to these fissure into these smaller droplets, it starts to shrink. But the droplets start to go out and out. So the whole periphery, the outer annular ring, has broken down into these small fragments, and the mother droplet shrinks. So this is how the Marangoni effect takes place. And in fact, when I was preparing for my presentation, I also remembered something that I read from Abul Kalam Azad, from his Ghubar-e Khatir. And this verse came to my mind, in which the second verse is really, really nice. Az lutmai do moj hababe damidast. That is, these bubbles are created, these droplets are created the by the waves, by waves. Yani talisme naksh bar abast zindagi, such as life is like a fleeting moment on the surface of water. Now we can do quantitative analysis. I put this into a software, I put this into PhysTrack, and I can count, and I can look at the evolution of the radius of the mother droplet and the daughter bigger outer periphery with time. So this is data from different students. So if I look at the outer radius, it keeps on increasing with time. And if I look at the mother droplet, it increases as we've explained, and then it starts to shrink. It coalesces into one another. So you can do a beautiful quantitative analysis of the shapes of the mother droplets and the outer peripheral big ring that is produced. And the great thing is that you can see universality in this data. This is all self-similar. If you discount the original, by the way, this data is for different concentrations of isopropanol above the 35% threshold. Below 35% threshold, you do not see the Marangoni effect. And this is so strange that this critical value of 35% is an analytical value that is derived from first principles. It's very seldom that you have problems in fluid mechanics in which you have something as neat as this. And if I were to do a normalization, so that I kind of look at all of this data and normalize it with respect to the maximum radius in that particular instance, all of this data coalesces onto the same curve. So I get this beautiful universality behavior, which is really, really, really interesting. So no matter what the initial concentration of the alcohol is, I get self-similar or universal behavior. Okay, so this is one of the most beautiful things that I find in this experiment.
सर 0.5 के बाद मतलब फर्दर रिदम इम्प्रूव इंक्रीज द कंसंट्रेशन ऑफ आईपीए तो अगर सपोज हम इसकी 0.70 या इससे वर्क करें, हैव यू एनी आइडिया कि क्या ये इफेक्ट डिस्ट्रॉय होना शुरू होगा या फर्दर एक्सटेंड
it
करेगा?
it becomes more chaotic, and it will be seen, but it will be hard to track it. So if you go beyond 50 or 60%, since alcohol is evaporating, and the evaporation of alcohol has a major role to play in this ridge instability, the process becomes so chaotic that it becomes almost impossible to measure it with the normal frame rate cameras that we have. You need a very high speed camera and a very high resolution camera to see those effects. Okay. So this data is taken with a DSLR at say about 40 or 50, maybe 100 frames per second at the most. So this is data from Vajahat from another area. So in another run of the experiment, you get the same behavior. We could of course also do diffusion studies, normal diffusion studies without the oil in a shallow film of water, and we can look at the diffusion and the Einstein's diffusion equation, and we get very good match of the data with the models. What we're trying to do now, and I wish I had some students who could do this. Now we would like to look at how the thickness of this mother droplet changes with time. So it's thicker in the middle, it's bulgier in the middle, and then kind of thins down, and it kind of then separates out into these droplets. So we would like to do a dynamic measurement of the thickness of this film, and we would like to do this with interferometric purposes. So one of our students who was a school student who tried doing an interferometric measurements like the neutral rings experiment, these are the kind of fringes that he saw. And this was another student, Sidra, who kind of so this is another video in which you can see the evolution of Michelson fringes. uh, and I just don't have the time to play this. Let me, it's very interesting. So here you can see these fringes, the Newton fringes kind of appear and disappear as evaporation is taking place and as the thickness of this film is evolving with time. So we want to do dynamic measurements of the thickness of this central drop. It's very hard to do unless you resort to an optical technique. So the last effect I would like to mention, and just take 3 or 4 minutes for this, is the Leidenfrost effect. And the Leidenfrost effect is really interesting. So if I have a liquid on a hot surface, then the there is a thin cushion of air that is formed between the hot surface and the liquid, with the help of which the liquid forms a blob, which of course whose shape is determined by the surface tension, and that blob kind of jumps on that cushion of air with very little friction. So you've seen this on your stoves when you kind of put a drop of water on an empty pan, it kind of jumps around. That's called the Leidenfrost effect. And this Leidenfrost effect is also a very complex phenomenon. So here, one of our students, in fact, another school students, because it's very hard for me to engage LUM students, but for some reason, non-LUM students would like to work with me. So this drop of water is on a very hot surface of, it's on a hot plate, and this drop of water is actually oscillating and breathing, and it's showing a particular size of the drop, and it's showing a particular breathing between a particular number of fingers. And you check this drop and you see how the number of these fingers changes. Okay, so now what we would like to do with this phenomenon is, I was actually inspired by this. For a long time, I had wondered what. So if you if you look at this image here on the left, this is from a movie. This is from a movie, and there is an actress who has an inverted cone in front of her. And I always wondered what could be the use of this inverted cone. But here you see, I'm trying to do an experiment with this inverted cone. So in this inverted cone, we put in liquid nitrogen, just really cold liquid into it, and what we see is that uh, drops of liquid oxygen coalesce on the outer surface. Now, if I kind of, sorry, I have to keep on shuttling between. So if you observe here, you can see drops of liquid oxygen They are formed on the tip of this cone, and these liquid oxygen drops fall down, and then they fall onto a flat surface. On that flat surface, we have a magnet, and they kind of these oxygen drops move around the magnet. मैग्नेट उस सरफेस के नीचे कहीं पड़ा हुआ है ठीक है सो So this is the copper cone, liquid nitrogen inside the copper cone. The air has oxygen. So the oxygen inside the ambient air has a higher boiling point than liquid nitrogen. Liquid nitrogen minus 196, liquid oxygen minus 183 degrees C. So the oxygen in the air condenses on the outer surface of the cone. All of this collects. It coalesces on the vertex of that cone, comes together as a drop, falls down onto this inclined plane, and it is shot out at a certain velocity onside this black sheet. And under that black sheet we have a magnet, and it kind of rotates around the magnet or kind of changes its depth. What experiment from 116 years ago can you recall which does something similar but at high energies, at the mega electron volt energies? Is there something similar that rings a bell? It's exactly the same kind of experiment that we're doing. Can you remember something from 1911, 1912? No. The Rutherford experiment. The Rutherford experiment with gold foils was really alpha particles shot at a gold nucleus. And the alpha particles, some of those alpha, most of the alpha particles went straight through, but a sizable fraction of those particles were deflected at some angle. And even some were bounced back, they were deflected backwards. So that was the electrostatic interaction between the nucleus and the alpha nucleus and the gold nucleus. But the alpha particle had an energy of about 4 to 5 mega electron volts in that experiment. Now here you have energy in the electron volt regime, much smaller energy, but exactly the same phenomenon, the same mechanics. The interaction, however, is now magnetic. It's not electrostatic; it's magnetic. So it's like a low energy version of the Rutherford experiment that we're trying to do. So now what you could do is you could kind of put a camera on top of it, and with phys track you can plot the trajectory of these drops and do a careful, rigorous analysis. Right. So here are some trajectories from some 6 or 7 drops, and you can define your angle, your distance of approach. You can write an equation of motion, which has kinetic energy part, which has rotational kinetic energy, which has angular part, and which has a magnetic part in it as well. You assume that your magnet acts like a dipole, so the energy has 1 over r6 dependence. Then you invoke the conservation of angular momentum, uh, and you come up with this equation. You also plot the magnetic field so that you have a profile of your magnetic energy density on the surface of this object. And then you do a careful analysis. You predict what angles should you get for the deflection. And here is the correspondent. The black points show our data, whereas the blue shows a theoretical model. And we get very good matches between the experimental data and the predicted models. Okay. So I think just the last slide. Here you go. So this is a close-up. Now, what I really like about this experiment is that it's, it's like the solar system. You have a comet coming in, and you have this massive object, and you can look at the trajectory. So you can find out the trajectory of this object, given the mass of this object, given the interaction. You know that oxygen is paramagnetic. That's why this effect does happen. And there's a magnetic field of this magnet. You look at the magnetic field surrounding this magnet and find out what the trajectory of this object should be. You can find out the velocities. You can see Kepler laws at work. You can see all kinds of gravitational laws at work. And we did something very nice. We can, I think this is the YouTube video. I don't know if it's going to play from here, but let me try. Let's entertain ourselves to a little bit of music as well. And that's my last. They can coalesce. Thank you very much.
Right. Do we have questions? If there are no questions, I'm going to hand out the quizzes. Because then everything is clear.
In case of pendulum, the noises which disturbing the signal and ENF, what are these noises? Are they in the vibration or the video tracking? We are doing?
I think these are the noise is just due to the fact that we cannot do a clean oscillation. There's always sideways tumble. The springs are not uniform. And this is not due to the video track. The video tracking is more powerful than the noise this is being presented to.
There may be because of the mechanical.
I think it's the mechanical jitter of this pendulum. So people go to lots of. So the Wilberforce pendulum is now a museum object, and people and instrument makers take a lot of pride and go to extreme lengths in making this coupling between the rotational part and the vibrational part vivid and conspicuous. So they make a Wilberforce pendulum that just stops oscillating and starts spinning very fast. But that's an engineering challenge. The great thing about our video tracking is that you do not have to make this into a visually appealing object. It's not a museum object, rather by just tracking the motion and looking at the nuances of the motion through video tracking, you can look at these avoided crossings. That's the beauty of this. We do not focus on the engineering part, rather we focus on the physics part.
सर एक आपने कोई प्लॉट दिखाया था ऑक्सीजन वगैरह फीडबैक उसमें एक एट द स्टार्टिंग पॉइंट वो फिजिकल एक्सपेक्टेंसी वाली
ये पहला था, ये था, फिर ये है।
हाँ जी सर वो स्टार्टिंग में क्यों डिस्क्रिपेंसी आ रही है
कौन से वाले? ये
He
वाला?
doesn't like the quality of your experiment. He's saying,
ये वाला?
ये यहाँ पर deviation आ रही है.
I'm just asking this physical वजह क्या है क्योंकि बाकी सब तो वो I think बहुत अच्छी तरह से फिट हुआ
मुझे इस पे देखना पड़ेगा, मुझे भी सही याद नहीं है। थ्योरेटिकल में देखें ना, ये नीचे से ना एक हम्प है और हमारे पास ये डेटा या लो बीज पे ना, ये जहाँ लो बीज है यानी अप्रोच, और बी क्या है हमारा, बी हमारी ये अप्रोच है, तो इस पे मुझे सोचना पड़ेगा, मुझे याद नहीं आ रहा कि क्यों है ऐसा। बाय द वे जो थ्योरेटिकल प्लॉट है ना, ये भी न्यूमेरिकली डिराइव हुआ हुआ, क्योंकि ये जो इक्वेशन ऑफ मोशन है असल में, ये जो इक्वेशन है ना, दिस इज obtained by setting r dot equal to 0. So you have a periradius, a peripheral radius, when r dot equals 0. So there is no radial motion, there is only angular turn. So at that point we derive this. So this solving this equation, solving this equation here gives you rp, which is the peripheral radius at which the angular displacement, the angular velocity, only angular velocity exists, and r dot does not exist. So there is no radial motion. That's the point of inflection where this liquid oxygen drop is kind of turning, purely turning. It's not moving radially outward. So this data is a plot of that peripheral radius. By the way, one thing that you shouldn't overlook in this experiment, which I find fascinating, is that you're making liquid oxygen. So this is fractional distillation of the air that you're trying to do. and and it is happening because of the gradient of the boiling point between liquid nitrogen and oxygen. Inside the cone is at a lower temperature. Outside the cone, of course, is a higher temperature. The brass has a particular finite conductivity. So outside, the temperature is higher than minus 196 degree, but still lower than minus 183 degrees centigrade. And that allows you 20% of the air is oxygen. So that allows all the oxygen to condense. It has, of course, some water vapor in it. So this is a beautiful demonstration that oxygen is paramagnetic as well. If it weren't paramagnetic, and we know that it has to be because no other gas would be deflected by a magnetic field. So it's a great way of making liquid oxygen inside the lab, just with liquid nitrogen. This is the beauty of thermodynamics as well. I think Walter would have appreciated this.
Right. Any other questions? Online audience, are there any questions? If so, please unmute yourself and go. We're just going to give you half a minute. In the meantime, people are welcome to ask questions.
सर एक क्वेश्चन पूछना चाह रही थी कि आपने वो भी मैरागोनी इफेक्ट का बताया था, उसमें लिक्विड की पोलैरिटी यानी दो डिफरेंट पोलैरिटी के लिक्विड्स हैं, उनका पोलैरिटी का कोई रोल है उसमें कि मतलब आप ड्रॉप को सेपरेट करें?
देखो, वाटर और अल्कोहल दोनों पोलर मॉलिक्यूल्स हैं, ठीक है, जबकि ऑयल है ओलिफेनिक है, वो नॉन पोलर है. एक्चुअली ऑयल के दो पार्ट, ऑयल नॉन पोलर है, ठीक है, इसलिए वाटर और अल्कोहल और ऑयल मिक्स नहीं होते. यही वजह है कि ड्रॉपलेट्स बन पाते हैं, यही वजह है कि वो ड्रॉपलेट्स मिल के एक कंटिन्यूम नहीं बना पाते, वो अलहदा हैं, अलहदा ही रहते हैं. एक्चुअली अगर आप उन वीडियोस के बिल्कुल आखिर में देखें, उन सब वीडियोस के आखिर में जिस तरह कॉन्डा इफेक्ट होता है कि आखिर में आप देखें बिल्कुल ना, ये देखें, ये जो आपको डाई, ये वाटर मॉलिक्यूल्स हैं, ये इकट्ठे कोलेस हो गए और ये पैटर्न्स बन गए. ये मिक्स नहीं हुआ, इस वजह से मिक्स नहीं हुआ क्योंकि ये ऑयल और, ठीक है, पीछे बर्तन भी करते हैं. तो मैरंगोनी इफेक्ट की स्पेक्टेकुलर ब्रिलियंस को देखने के लिए ही हमने वो ऑयल में डाला.
Any other question? If not, then let's thank the speaker. And thank you everybody for attending.